Hi, my name is David Schultz. Welcome to Our Earth, its climate, history, and processes. Today we want to talk about earthquakes and seismic waves. Earthquakes are disturbances in the solid earth that lead to seismic waves rippling away from the disturbance. The point at which the disturbance happens is called the focus, and the point directly above this focus on the Earth's surface is called the epicenter. These seismic waves can be created by a number of different processes. First, they could be created by the relative movement of one piece of the Earth's crust past another. This would lead to friction against these two plates, creating the waves. You may also have an underground magma chamber, and as this magma starts trying to flow into the surrounding rock, lead to seismic waves. And you may have underwater landslides that create seismic disturbances that then radiate away from the point where the landslide occurred. Large earthquakes are relatively rare, but there are hundreds of smaller earthquakes every year around the world. On any given day, there are about 5 earthquakes around the world that are capable of producing damage. These seismic waves are detected by a global network of seismometers, instruments that measure the sensitive vibrations of the Earth. By triangulating the arrival of seismic waves at these different seismometers, you can locate where the origin of the earthquake happened. There are many websites that you can find online that will plot most recent earthquake activity, and I've given you several here on this slide that you can look at. We measure the intensity of earthquakes through a variety of different measures. One of these measures is called the Richter scale. The Richter scale represents the amplitude of the shaking, but it's a logarithmic scale. So for instance, as you go from Richter 5 to Richter 6 on this scale, you increase the amplitude of the waves by a factor of 10. Now the energy contained within these waves are equivalent to the square root of the cube power of the difference. So as you go from a magnitude 5 on the Richter scale to a magnitude 6, this is a factor of 10 in amplitude, but this is equivalent to 31.6 times the energy released. So you can see that this is a highly nonlinear relationship. As the Richter scale increases by just an increment, then the energy goes up quite substantially. An earthquake is classified by the depth of its focus. In other words, how deep in the earth does it originate? Shallow earthquakes are less than 20 kilometers deep. A deep focus earthquake is often associated with subduction zones. As we'll see later in the course, a subduction zone is where one plate of the Earth's crust is going underneath the other. The maximum depth that we find earthquakes tends to be around 700 kilometers below the Earth's surface. These earthquakes commonly occur across faults, as I mentioned before. How does the movement across these faults take place? After the 1906 earthquake, Henry Fielding Reid was studying the fault patterns and the devastation that occurred, and he came up with the elastic rebound theory. The idea here is that under the force of stress being applied to the Earth's crust, the Earth would deform and eventually reach a breaking point, at which point the rupture would occur, and that rupture would be the earthquake. So this rupture then would occur across fault, and that would be where the breakage occurs. So in this graph here, you can see over time a region of the Earth's crust being applied a continuous stress across this fault. As the stress increases, eventually the point where you reach the limit of the strength of the rock to withhold this, to withstand this stress occurs, and then an earthquake happens, releasing the stress. Not necessarily back down to zero, but it has reduced the amount of stress. As the stress continues to build again, eventually you may reach that point of strength of the rock being exceeded again, and you get another quake. And this could be ongoing for many cycles. So given this plot, you might think then that earthquakes could be pretty repeatable, that as if the amount of stress applied is constant, you would see, and the rock strength remains fixed, then these two quantities would lead to a predictability in the earthquakes. But we know that this isn't necessarily the case. First, the application of the stress across the fault may not be constant over time for various reasons. We also know that the local rock strength is not necessarily constant either. For instance, along the San Andreas Fault, it's not just a single fault, but there are many smaller faults that comprise this fault system. As the stress is released on one of these faults, the stress may be shifted onto another fault. And so there's no simple way to measure the rock strength. And so you may see then stress being applied from one of these smaller faults to another. So the result is that earthquake prediction is not as simple as weather prediction. We don't have any observations of the stress underground. That's not an easy quantity to measure, nor do we know necessarily what the strength of the rock is. And we may not even have fully mapped the suite of faults that occur within a fault system. After an earthquake occurs, waves are transmitted away from the disturbance, releasing that energy away from the earthquake. There are three types of waves that transmit this energy away from the focus. The first one is called a P wave, or a primary wave. The second one is called the S wave, or the secondary wave. And the third one is called the surface waves. The P waves, or the primary waves, are compressional waves. They're like sound waves. The energy is being moved in this direction, and the material is being compressed and expanded as the wave proceeds, and this energy then is transmitted in this direction. Primary waves travel through solid surfaces, but they also travel, as you know, through liquids and gases as well. These are the fastest seismic waves, and they travel at a rate that's proportional to the density in which they're traveling. S waves, or secondary waves, are also called shear waves or transverse waves. In this case, rather than the displacement being in the direction of motion, the displacement of the wave is perpendicular to the direction of motion of the wave. That's why we call them transverse waves. S waves travel about half the speed of the primary waves. Moreover, they don't travel through liquids and gases. They only travel through solids. And this is a key point that we'll see later that tells us about the structure of the interior of the Earth. The third type of wave are called surface waves. These are like ripples on the surface of the land. They can travel through liquids and solids. When an earthquake occurs, the seismic waves are radiated out away from the focus. These waves, however, do not travel in a straight line necessarily. Due to variations in density or the composition of the substance that it's traveling through away from the focus, the waves may be bent or refracted. where a material is denser, the wave will be bent away from the denser material. And so, as we see in this cross-section of the Earth and a near-surface seismic disturbance causing P waves to emanate from this disturbance, we see that these waves are curved. And they're curved upward, away from the denser material near the center of the Earth. Sometimes these seismic waves may hit internal boundaries within the Earth, say between different layers or different compositions within the Earth. So then you may have reflections both upward and away from this interior surface. So you end up with a very complicated pattern of waves after an earthquake being transmitted through the Earth and being detected from the global network of seismometers. You can use this pattern of waves, all the reflections, all the arrival times between the P waves and the S waves, to image the interior of the Earth. And so even though we've never drilled down more than a few kilometers deep into the Earth's crust, we know a lot about the interior of the Earth. And one of the ways we know about that is through the detection of seismic waves and their reflections and refractions that we can infer from these boundaries, these layers within the interior of the Earth. In this graph, what we see is a plot of the P and S wave velocities as a function of depth within the Earth. And you can see different layers labeled here as a function of depth. The speed of these waves increase rapidly as you go down through the crust into the mantle to a maximum value for the P waves of about almost 14 kilometers per second. And this is a reflection of the higher density within the mantle, leading to faster wave propagation. As you get to the outer core, the wave speed drops due to the fact that the outer core is now a liquid, and the S wave velocity actually goes to zero. As we've said before, the S waves do not travel through the liquid outer core. So to summarize today's lecture, if we look at the Richter scale, which is a measure of the intensity of a seismic disturbance, we know that it's a nonlinear scale. For each increment that the Richter scale goes up, we have a factor of 10 amplitude, but that factor of 10 amplitude increase leads to a factor of 31 in terms of the amount of energy released. We know that earthquakes occur along a variety of depths, and that the deep focus earthquakes tend to occur along subduction zones. We learned about the three different types of seismic waves, the P and the S waves in particular. The P waves travel twice as fast as the S waves, but the S waves don't travel through liquids. And then finally, we learned that by measuring the arrival times of the waves, the structures and amplitudes of these waves around the world, that we can model what the interior of the Earth looks like. In the next lecture, we will talk more about this structure and how we know about the interior composition of the Earth.